Have you ever wondered why earthquakes, one of nature's most terrifying events, are so unpredictable? You see, while we've made significant strides in understanding the mechanisms that trigger these seismic events, predicting the exact time and location of an earthquake remains a daunting challenge. The reasons for this are as complex and diverse as the earthquakes themselves. Firstly, let's consider the fact that earthquakes aren't a one-size-fits-all kind of phenomenon. They can range from barely perceptible tremors to devastating shakes that can level entire cities. This enormous variability is due to the complex nature of seismic activity. Earthquakes are caused by the sudden release of energy in the Earth's crust, resulting in seismic waves that shake the ground. The amount of energy released and the manner in which it's released varies greatly from one earthquake to another. Moreover, the Earth's crust isn't a uniform slab of rock. It's a patchwork of different geological formations, each with its own unique properties. This means that seismic waves can travel in unpredictable ways, making it difficult to accurately predict where an earthquake will strike or how intense it will be. Another critical factor is the limitation of our current prediction models. While these models have greatly improved over the years, they're still far from perfect. They're based on historical data and geological observations which, while useful, can't account for all the variables at play in an earthquake. For example, they can't predict the exact moment when the stress on a fault line will reach a breaking point triggering an earthquake. And then there's the issue of scale. Earthquakes can occur anywhere on Earth, from the deepest ocean trenches to the highest mountain peaks. This vast geographical spread further complicates the task of prediction. So, despite our best efforts and the amazing technological advancements we've made, earthquakes remain an unpredictable force of nature. This unpredictability is a stark reminder of our planet's dynamic nature and our ongoing quest to better understand it. Can the Earth give us subtle hints before an earthquake strikes? Now, this is a question scientists have been pondering for decades, and one possible answer lies in the concept of foreshocks. These are minor tremors that sometimes precede a larger earthquake. Imagine them as the Earth's way of stretching its muscles before a big race. Foreshocks can be likened to the quiet whispers of the Earth, a potential warning sign of a more significant seismic event. But not all earthquakes are preluded by these whispers. Some earthquakes burst onto the scene without any forewarning, making them even more unpredictable. However, when foreshocks do occur, they provide valuable insights into the Earth's seismic activity. Scientists can study these minor tremors, hoping to glean some understanding of what might come next. So, while foreshocks may not be a surefire warning sign, they can act as nature's subtle prelude to the main event. They remind us that even though we can't predict earthquakes with absolute certainty, we can still learn from the Earth's subtle signs. How do we measure the shaking intensity of an earthquake? Well, there are two main scales we use. The first is the Richter scale, named after Charles F. Richter. This scale quantifies the energy released during an earthquake. It's logarithmic, meaning each whole number increase corresponds to a 10-fold increase in measured amplitude, and roughly 31.5 times more energy release. For example, a magnitude 5 earthquake releases 31.5 times more energy than a magnitude 4. But the Richter scale doesn't tell the whole story. Enter the modified Mercalli scale. Unlike the Richter scale, the modified Mercalli scale measures the perceived shaking and damage caused by an earthquake. It's a subjective scale using eyewitness accounts and damage assessments to rank an earthquake's intensity from 1, being not felt, to 12, total destruction. Thus, the Richter and modified Mercalli scales give us a way to quantify the often devastating power of earthquakes. Did you know that earthquakes can trigger massive waves known as tsunamis? That's right. When an earthquake occurs beneath the ocean floor, it can displace colossal volumes of water, setting off a chain reaction that can lead to tsunamis. Imagine a sudden jolt beneath the sea surface. It's like dropping a stone into a pond, but on a gigantic scale. The energy from the earthquake pushes the water above, creating ripples that can grow into towering walls of water as they approach the coast. These tsunamis, unlike regular waves, can travel at high speeds across the ocean, maintaining their energy over vast distances. When they eventually reach coastal regions, they can cause widespread devastation, engulfing entire towns and cities, disrupting lives and economies. The destructive potential of tsunamis is immense, and they serve as a stark reminder of the far-reaching impacts of undersea earthquakes. So, the effects of an earthquake can extend far beyond the epicenter, reaching even distant shores. Can humans cause earthquakes? A question that sounds like it's straight out of a science fiction novel. Yet, the answer is a surprising yes. Human activities such as mining, reservoir-induced seismicity, and hydraulic fracturing, also known as fracking, can indeed induce seismic activity. This phenomenon is known as induced seismicity. Let's take a closer look. Mining, for instance, involves the extraction of vast amounts of earth. This can cause a shift in the stress within the Earth's crust, leading to ground instability and, yes, even earthquakes. In fact, some of the most high-profile mining-induced seismic events have registered magnitudes over 5 on the Richter scale, comparable to a moderate natural earthquake. Reservoir-induced seismicity, on the other hand, happens when large amounts of water are stored behind dams. The weight of this water can increase stress in the Earth's crust, leading to seismic activity. The most infamous of such incidents is the Oroville Dam earthquake in California in the late 20th century. Then there's hydraulic fracturing or fracking, a method used to extract oil and gas from deep within the earth. The process involves injecting high-pressure fluids into a well, creating small fractures in the rock that allow oil or gas to flow out. This high-pressure injection can cause small earthquakes, and in some rare cases larger ones. So when we talk about induced seismicity, we're referring to earthquakes and seismic events that occur as a direct result of human activities. It's crucial to note that these are not the same as natural earthquakes, which are caused by tectonic processes within the Earth. However, they can be just as destructive, potentially causing significant damage to structures and posing a threat to human life. In conclusion, while many earthquakes are purely natural phenomena resulting from the Earth's own dynamic processes, our actions can sometimes tip the balance. We must remain aware of our impact on the planet, as even the ground beneath our feet can respond to our touch. Thus, while earthquakes are a natural phenomenon, our actions can sometimes tip the balance. How does the threat of earthquakes influence our building's design? Let's delve into this fascinating intersection of nature and human ingenuity. In regions prone to seismic activity, the threat of earthquakes heavily influences architectural design. Architects and engineers must essentially play a high-stakes game of chess with Mother Nature, predicting her moves and designing structures that can withstand her power. This is where the principles of earthquake-resistant design come into play. These principles guide the creation of buildings that can absorb and dissipate seismic energy to prevent catastrophic collapse. For instance, buildings are often designed to sway with an earthquake's motion, rather than resist it. This is achieved through various techniques such as base isolation, where a building essentially floats on flexible pads, and energy dissipation devices, which absorb seismic energy. But it's not just about the buildings themselves. The surrounding environment, including soil and slope conditions, also plays a crucial role. Architects must take these factors into account, adapting their designs to the unique challenges each location presents. Why is all this important? Because it saves lives. Earthquake-resistant designs ensure that when the earth shakes, buildings stay standing, providing a vital shield against the destructive power of earthquakes. In this way, our understanding of earthquakes plays a vital role in creating safer living spaces. To summarize, earthquakes are a fascinating and complex natural phenomenon. We've explored their unpredictable nature, reminding us that despite advancements in technology, we are still unable to accurately predict when an earthquake will occur. We've delved into the concept of foreshocks, those minor tremors that sometimes precede a major quake, yet remain elusive and unpredictable. We also examined the measurement scales used to quantify the intensity of the Earth's shaking, the Richter and Mercalli scales, each portraying a unique perspective on an earthquake's power and impact on our lives and the environment. We ventured beneath the ocean's surface, where undersea earthquakes have the potential to trigger tsunamis, adding another layer of complexity and danger to these seismic events. We also addressed the concept of induced seismicity, the human activities that can unintentionally trigger earthquakes, reminding us of our profound impact on the Earth. Finally, we looked at how earthquakes influence architectural design. We saw how engineers and architects around the world incorporate seismic considerations into their designs, making buildings more resilient and capable of withstanding the Earth's powerful tremors. Understanding earthquakes not only satisfies our curiosity, but also helps us prepare better for these inevitable events, making our world a safer place.